Hey everybody, this is Polar Unit Video 10 on the nth root theorem. Alright, so you've got your note sheet ready, and I want to kind of put this out there before we get started. The nth root theorem is going to be one of those topics that I'm going to give you a lot of procedure on here, and we're going to get to talk more in class about the why and the how come and that. So when you finish this video, if you're still left with, great, I got some numbers but I don't know what they mean, then I understand that that may be exactly where you're sitting, because I think it'd be best if we got to talk about all of the whys in class. So with that in mind, you relax on that part as long as you can follow the procedure right now. We'll get to talk more about a little bit more in depth while we're in class together. So an nth root. For a positive integer n, the complex number a plus bi is an nth root of the complex number x plus yi if. So I'm going to take whatever this positive integer n is, maybe it's a 2 or a 3 or a 4, then the outcome, I don't know where that comes from. So I want a plus bi to a certain power, and these are nth roots. And so I'm going to explain the process of that. But this term nth roots we've seen before. You may have had the cube root of 27. That's an nth root. The fifth root of 32, or even the cube root of a negative number would work as well. So we could type these into our calculators using a button under math. Look under math and you'll see this x root for the parentheses, and you could put in your number there. Or you can type it in as an exponent, and you must use parentheses then. Oops, that should be 27. The answer is 2. Or 3. And then the answer to this one is 3. Here, this is the fifth root. Oh my goodness. It's the fifth root . Alright, so let's get started. The nth root is, for any positive integer n, the complex number a plus bi is an nth root of the complex number x plus yi. So I'm taking this exponent and we're raising it to a power, any positive integer, whole number, power. So where have we seen the nth roots before? We actually saw them in Algebra 2. For example, if you had the cube root of 27, or the fifth root of 32, or we could even do the cube root of negative numbers as well. So in your calculator, you can enter these under the math button, and there is a cube root button, but there's also this x root button, and that takes care of ones like the fifth or the fourth roots. You may also enter them using exponents. This is 27 to the 1/3 power. If you choose to enter it into your calculator this way, you'll need to use parentheses around your exponent, so after the caret. Here, this is 32 to the 1/5 power, and this one's -8. You must use parentheses to the 1/3 power. So what are the outcomes? Well, we're looking for a number that when you multiply it by itself 3 times or 5 times or 4 times, that will give you this number under the radical. So this one is 3. The fifth root of 32 is 2. And this one is -2. Okay, so let's take a look. All right, for the cube roots of the complex number 8, I'm going to write it in shorthand, cis 135, we're looking for a complex number, this guy, that after we cube it gives us that outcome. So the goal is that we're looking for what was already being cubed. What was the thing that got cubed? Well, if we think about de Moivre's theorem, I end up with r cubed in shorthand cis of 3 theta. So the parts we have to figure out are what are the angle values, and then what do we have for our r value? Well, our r value is always going to be the easiest to figure out. R cubed equals 8, which means we wanted the cube root of 8, or 2. So we've got the r value we're going to need. Then we have to find the theta value. So this part's a little bit trickier. Okay, so if I consider the fact that I want my 3 theta to equal a coterminal angle with 135, then I'm going to multiply it by I'm going to add on 360 because I'm looking for coterminal angles. You're like, well, all of my angles are coterminal if I just add 360, except that I'm going to be dividing by 3 because I really just want the theta. I just want the angle. So I'm going to take this right here to my next screen. So I had that theta equaled 135 plus 360 times some value of k. Well, k is always going to be any integer, positive integer. So in this case, and I'll explain in a moment why we're using this, I'm going to use k equals 0, k equals 1, and k equals 2. So I'm looking at the angle that's going to occur when I have 135 plus absolutely no rotations divided by 3. I'm going to do 135 plus 1 rotation divided by 3, and 135 plus 2 rotations divided by 3. So why did I stop at 2? Well, after I calculate these, we'll discuss why I chose 0, 1, and 2. So calculate these using your calculator. Make sure that you enter the entire numerator, hit enter, and then do divide by 3. The first one comes out to 45 degrees, the second one 165 degrees, and the last one 285 degrees. Now the reason I chose not to do k equals 3, k equals 4, k equals 5, and keep going is because as soon as I do k equals 3, I get the answer that theta would equal 405 degrees. Well, 405 degrees is actually 45. And if I did k equals 4, then that would give me the angle value of 525, which if I subtract 360 is 165. So you'll see that k equals 5 will give me this, and then k equals 6, 7, 8, and it'll just continue, and I will end up with these 3 angles just by subtracting additional rotation. So these are the numbers I need. So what is my answer? Well, my answer we were looking for is what polar number can you have that if I cube it would get me back to my original 8 cis 135. So we decided our R value is 2, and now I have 3 outcomes. And these are my 3 final answers. These are my cube roots. If I were to apply de Moivre's theorem and cube each one of these, we know our number in front would become an 8. And if you multiply 45 times 3, you'll get 135. If you multiply 165 times 3 using de Moivre's theorem, I would get an angle that was coterminal to 135 by just subtracting a rotation of 360. If I multiply 285 by 3, I would have to subtract 2 rotations of 360, and I would get 135. So all 3 of these angles using de Moivre's are going to be coterminal with 135. Okay, so in summary here, I'm looking to take the cube root of my R value, or the nth root if we're using a different one. And this is the formula I gave you. It's to find those smaller angle values that are coterminal with the one that we want. Okay, my k values are going to be integers, and it'll always be one less than the number of roots you're looking for. So if I'm looking for 5 roots, I'm going to use 0, 1, 2, 3, 4. Okay, if I'm looking for 7 roots, I'm using 0 through 6. It's always one less. So let's try another one together. This one, I want to take the 4th root of 16 to find my n value, which also happens to be 2 for this problem. And this time, I'm going to use, because I want 4th roots, I'm using I'm going to use alpha to represent a different angle, equals 60 plus 360k divided by 4. Now the k values I'm going to use are k equals 0, 1, 2, and 3. So let's try it. 60 plus 360 times 0 divided by 4. 60 plus 360 times 1 divided by 4. 60 plus 360 times 2 divided by 4. And 60 plus 360 times 3 divided by 4. These will give me my 4 angle values. So the first one gets me 15 degrees, the second 105 degrees, the third 195 degrees, and the fourth 285 degrees. So my answers are 2 cis 15, 2 cis 105, 2 cis 195, and 2 cis 285. Now think carefully about this, because if I were to subtract the difference between each of those angles, it has something very, very much related to being a fourth root. Think carefully, and we can talk about that tomorrow. If you discover what I mean by what's the difference between these angle values and why it's connected to being a fourth root, you may post that as a comment. Let's try another example together. I want to find the fifth roots of this. Now, actually, I'm going to change this. I don't want to use that one, so change this in your notes. I want to use the square root minus I, square root of 2 minus the square root of I root 2. Okay, we get a little bit better of an R value when we do this. Well, I need to put this in polar form, first of all. So let's start with R equals the square root of the square root of 2 squared plus the square root of 2 squared, which will give me the square root of 4, or 2. Now I haven't yet done anything with my nth root theorem. That's just the R value for the original problem. Next, let's find the angle value. Well, if both of these values, x and y, are the same, I know it's a 45, and because of the positive and then a negative, I know it's also in the fourth quadrant. So that gives me that this turns into polar form as 2 cis 315 degrees. All right, now we have to start the nth root theorem. Well, I want the fifth root, which means I want the fifth root of 2. And there's no fifth root of 2. That's beautiful. So we're going to leave all of our R values as the fifth root of 2. Now let's get into the angle values. So to do the angles, I want k equals 0, 1, 2, 3, and 4. It's always one less than the one I'm looking for because that gives me 5. So this is going to be 315 plus 360 times 0 divided by 5. 315 plus 360 times 1 divided by 5. 315 plus 360 times 2 divided by 5. 315 plus 360 times 3 divided by 5. And 315 plus 360 times 4 divided by 5. So I'll give you whatever time you need to pause it and go ahead and calculate those, or you can follow along and trust that I've done it correctly. I got 63, 135, 207, 279 degrees, and 351 degrees. Okay, and those are my values. Now to write my final answers for all of these, I will simply write the fifth root of 2 cis 63 degrees, the fifth root of 2 cis 135 degrees, the fifth root of 2 cis 207, the fifth root of 2 cis 279, and the fifth root of 2 cis 351 degrees. Again, if you look at the difference between these, see if you can make a connection to the fifth root, and that finishes that problem. These are our 5 fifth roots. Okay, so I'd like you to try this one on your own. You will have to first convert this to polar form, and then you need to then find your new, so you're basically undoing de Moivre's theorem. Oops, So you need to undo his theorem. So if you try that one on your own, and then we'll take a look at it together.